Hello everybody, today we have a look at a map, my favorite container by the way. So how would we have our decision to go to a map? As always, you can here right click to get the links. Yeah, we need to handle game data. Normally we handle it in a struct or an object. Then if the data are transactional, so if they are moving, being changed, then I go down the tree, otherwise I stay with the data table. Here are all data that will not change easily, small data, otherwise use a database. If there's a first in, first out need, so a queue, I obviously go to a queue. There are also some variants like circular queue with a fixed size, but queue very handy if you have that pattern. Is the uniqueness enforced? So do I want to have the data being unique? Then the set is the great way to go, but that needs a hash value above all structs or objects. Do I need order, like ranking or something like that, or I want to iterate in a certain direction? That is an array definitely. But in all other cases, really, I use a TMap. Map either as multi-map, so one value, one key, multiple values, or one key, one value. So how's the map structure and what can we do with it? So as I said, it's one value per key, meaning the keys are unique. It can either be actually a struct that generates a hash value, or it can be a GeoID, that is what I normally use as a value. But as long as it generates a hash value, you can use everything here. For the key, sorry. The value can be the same or different, that doesn't matter. Important thing is really just the key being unique. And if you don't have any, just use a GeoID, what I use here in the example soon. Yeah, if you have a lot of adds and remove and find operations, then the map is definitely something better than using an array. But they are of course related. They all at the end are kind of linked list, so they can be exchanged to a certain degree. But yeah, it's important to use the right one to be not too slow. What kind of functions do we have? Yeah, we have add item, remove item, obviously. We can get one key or all keys or all values. We can get kind of descriptive functions like what's the number of values, and we can empty the whole map, reserving capability or capacity for the next map. We can iterate over the map. I will show two examples, one with parallel iteration, one for standard iteration. I can sort all the keys and I can sort all the values with different sorting algorithms. And now let's have a look how to use it. First, I construct an object from class. The class in my case is TMap. That is what I get from the Pastebin. You see here with the green key like a key value store. And that would be my map to be saved here. Then I use the cities data table that I used in the last example also. That's just a data table showing 41K of different cities with their population. That's nice to have a kind of demo set here. So we use that and do some filtering and so on. So that is what we want to load, and we want to load it obviously into a map. So for the 41K cities, I just add the item. It's a different struct that I stored here, so I have to break it up and create my new map test struct, adding a GeoID. Then some descriptive things. First thing, I look at the number of values, and I would expect 41K. Then I can do a custom filter. I define the filter that takes a population value and gives you everything above it. So in this case, we give it 2 million, and we want to have it's actually 20 million. We want to have all the cities being larger than 20 million, and that these cities should then be printed out. No? So a simple example to filter something. And at the end, we have these two iterations. That is, one is the standard iteration. The other one is a ParallelForEach iteration. Let's have a look how that looks until now. Let's clear here and filter for TMap. Then we see a bit easier what happens. Let's go. Okay, let's have a look at the log. It's a bit small. Hopefully you can read 41K of cities, and we have 10 or so cities that are above 20 million. So yeah, loading is working, filtering is working. Let's have a look at the iterations here. What I do actually, I go through all the cities and add some strings to the name just to have something to do within the iteration. And for parallel, I do the very same, but with multi-threading. Let's run that. And you see here the magenta printings. We have about 400 CPU cycles for the parallel iteration, and it takes about 5,000 CPU cycles for the standard iteration. So that's dramatic. It's about 10 times faster doing it in parallel for each than in standard. there's some caveat. We will have to look into the C++ class to see what's going on and what we want to do here. Yeah, here's the overview of all the functions that you saw also in the presentation. What I did not demonstrate is here the sorting. That's also quite simple. Interesting here is really how to make that different sorting algorithms available in Blueprint. We will have a look at that. Here's the Pastebin. As always, you can directly copy paste that really into your class. I always do this from the outside world, not from within Unreal. That's kind of more stable, I think. So I clean up my directory here. I then go to my source folder. In this case, I have a plugin here. And here in the public, I just define my map. It's just really copying that one into the tmap.h or whatever file name you want to use. You see here, we have the map class and all the functions that we now will run through and have a look. First thing, the name needs to be the very same name as generated here. So this TMap generated H has to fit your name. And as it's always just one special structure that you use, you have to, I think, mostly create multiple maps. The timer class comes from Ilero. Have a look at that link, especially the first one. It's an extremely interesting article about this topic here. And that is just measuring the CPU cycles from start to stop. Then we have this small enum that you just saw in the blueprint that is telling what kind of sorting do we want to have. So that's an easy way to define the sorting blueprint. So we have the enumeration here. The struct is the thing that is stored in the map. As always, the map can be initialized only with one special struct or object, meaning that is the one that we want to use here. It's the name number thing that we used in the other examples and with a GUI ID. This is the sorting, these are the sorting mechanisms. They are always static bool and return a bool like a comparison of two numbers, for example. We have that one delegate that gives you back a map test struct, meaning the one that was added or removed. Then we have the constructor not doing anything. The deconstructor is just really cleaning, resetting the map. And we have two delegate variables that are used, one for adding, one for deleting. Both are returning whatever was added or deleted for easier reference in Blueprint. And that should be map, not philostack. Oops, sorry. Just changing that one here. Okay, now we have the TMap itself. It's initialized always with a key and value. The key being in GUID, the value, the map test struct. Then we have public functions. One, of course, is adding and removing. Adding is really just adding the key and the value. And if the broadcast flag is set, we will broadcast that for Blueprint to have. Here with the remove, we actually want to also broadcast what we have removed. So we use here remove and copy value, not only remove, because we want to have that value and want to broadcast it that it was removed. So we can react to it. Okay, that was remove and add. Then we have a couple of MISC functions, like just getting the number of values that are here, or emptying the map, reserving some capacity for the new map, so not releasing the memory and then reclaiming it, but just getting it here. Then we have, of course, getting a single value from the map. I provide a GUID, as this is my key, and then I find the reference to it and return it. I can, of course, also get back all the keys if I want to iterate for them or something. So I use this generate key array that comes from the map, and the same with the values, generate value array. That's also quite easy to use, getting all the values. Now an interesting one, that is the filter. The filter takes a predicate, that is this filter by predicate here, and uses this provided population to compare it against the population of the regarding city. So we pass the population here in this brackets as a parameter being available in the lambda, and we get a single t pair, because a single entry in a map is always a pair, and the pair is a GUID and our test struct. And then we just compare the test struct, the key value pair test struct number with the population and give back a boolean. And we saw that was filtering, for example, everything above 2 million. Sorting, also quite simple. The value sort is getting this enumeration that we saw also in the blueprint that we can select. And then we just switch over it and call one of the static functions of the map as our sorting mechanism. So we just say value sort, and then we don't define it here because it doesn't really belong in the map class, but it belongs to the struct. The struct itself owns the logic if it's bigger or smaller than another struct. So we have this region sorting here, giving back always a bool, static function, and comparing two instances of this map test struct and returning a value, a bool value. And that is what we have here. That's very elegant to formulate and to read. The key sort is actually, we don't have, for the GeoID, we don't have a clear sorting mechanism, so we just compare the strings and say what's bigger and smaller. So we can also here sort the keys, but there's also custom logic here. So we can, in theory, also use a struct as a key and use the sorting there. Now let's have a look at the iteration. That's interesting, and we have to look a bit deeper here. We saw we have these two functions here, the standard iterate and the ParallelForEach. And you remember the one was about 300, the other one was more than 3000. So parallelization makes it 10 times faster, and that is great. That is what we want, but it's not actually that easy. So just let's have a look at the standard iteration. First thing, we take the prefix and copy it into a local variable. Then we start actually our timer. Then we get all the keys, iterate over all the keys, finding a value for each of the key. If the value is valid, we insert some string here. We just insert something into the name to do something here. Doesn't make much sense. And that is where we get around 3000 or so CPU cycles for the 41K. Very good. Now we do the same with parallel iteration. Same thing, local value for prefix. We get all the keys. Here we generate an F critical section mutex, and then we parallel iterate over them. We give into the lambda the prefix to be available, and we have as a parameter an int 32 for the entry that we are working on. Then we get the value, just finding one value according to a key, and if the value is valid, we again insert here some string. Here's a flag where different parallel modes can be tested. Not working here. You can switch around. It was not a big difference when I tried it out. So kind of the same logic, and that, as we saw, is very, very fast. Just kind of 10% of the standard iteration, 300 to 3000. That's great. One thing here, the scope lock is locking down the value that we're adding in here until the next bracket kind of. So the next line really is locked now. Let's have a look here. If we lock down, because that is what we should do, because multi-threading could mean that another thread is writing into exactly that value. So let's recompile here with the scope lock enabled and rerun it. And now we have actually 25,000 for the parallel and 5,000 for the standard. So it's 5 times longer, meaning the whole locking is extremely inefficient here with that map, with the current setup. And that is something that you really have to try out and think about. Where do you lock? When can you lock? When does it make sense? So I'm coming to the end here. We have a couple of standard containers that we discussed how to expose to Blueprint. The presentation is linked. You see again all my reasonings kind of summarized when I use what normally. It's absolutely makes sense to really think about it and make your logic much more powerful in your blueprints, much more cleaned up. I like blueprints. But yeah, some things should be done in C++. With the here link is always the Pastebin that you can start your blueprint with, or your C++ class with. And yeah, that's it. I hope the series helped a bit and was fun making it. Thank you very much for listening. Bye.